Hello. Hi. I hope you have enjoyed that movie. So that was just a preview of a story that later we're going to have Prashant tell you exactly what that story was about. But it was kind of a little preview just to pique your interest. Good afternoon. My name is Anni, and welcome to our unified, highly scalable platform for edge and cloud in 5G. So pretty much throughout this whole day, you've heard that we're going through this fast growth of 5G and edge computing. And then on top of that, we have AI, AR, VR, IoT, and metaverse even. Oh, these technologies are triggering this exciting development of the new era of digital services for today and maybe even for the future. And what's really running this exciting digital services is the cloud and network infrastructure. And so we think, our project team, we think that with the coming of 5G and edge, the existing cloud infrastructure today, especially the open source ones out there, are not going to satisfy the requirements of this, 5G and edge computing, AI kind of workloads. So we need to, if not redesign, but at least at very minimal, we need to extensively enhance the cloud platform in order to support this kind of 5G, AI kind of workloads. And this new cloud infrastructure needs to be highly scalable. And when we say highly scalable, it's not just hundreds of nodes per cluster. We're talking about hundreds of thousands of nodes, pretty much a hyperscaler level of the cloud platform. And it needs to be high performing with low latency. It needs to have a distributed architecture. And as you know, that a lot of this kind of 5G workloads run in a distributed environment. And edge computing, obviously, today you've heard that it's very important. A lot of, cinematographic rendering, neural rendering, AI, AI inferencing work has to be done on the edge side instead of on the data center side for resource efficiency, for the latency, and for, sometimes for security purposes. And also, this new architecture needs to support AI, obviously. And last but not least, it needs to support the newest way, the modern way of application development, which is cloud native, serverless. And don't forget, security is also very important. So with that, so about 2 years ago, we launched this open source project under Linux Foundation called Centaurus Project. It's designed to be a highly scalable distributed cloud framework. And with that, I'm going to invite the chair of the Centaurus TSC, Deepak, to go over the more details about the Centaurus project. Thank you.
Thanks, Annie. Hi, my name is Deepak Vej, and I'm part of the Futurewei Cloud Lab based out of Santa Clara. So I'm going to talk about Project Centaurus. So this is an open source project which came out of our lab. We built it out about a year and a half ago and donated it to Linux Foundation. So this is so very highly scalable. The reason you would think, why would you want to build a new cloud infrastructure project? Kubernetes is there, OpenStack is there. So we saw a lot of challenges. And this is, so I'll kind of get into that, what those challenges are. But the key goal is this infrastructure project, cloud infrastructure project, is a key enabler for the emerging application landscape, such as, AI, ML, or, metaverse or 5G applications. So because the key thing is for all of those applications, there's a huge need for, the scalability, low latency. So that's what this infrastructure project addresses. Yeah, so Centaurus is an open source project built towards building unified and highly scalable public or private distributed cloud infrastructure. So essentially, it's uniform resource management and uniform resource orchestration layer, actually. So abstraction as a single pane of glass, actually. So it doesn't matter what type of workload you deploy. It could be a container, it could be a VM, or it could be a unikernels or WASM WebAssembly. So it's essentially one single pane of glass. You deploy your workload in a uniform way. So that's the kind of a key thing. And as I mentioned before, aims to meet the challenges for the new types of workloads such as AI, 5G application landscape. So these applications, they have very unique characteristics, so such as, they are very different than traditional applications. Things such as, low latency is the key need for such applications. Mobility, the location awareness, and the security and privacy. So all of these things, they need to be addressed. So that's one of the goals is for us to be able to support these applications by addressing all these needs. Offers enterprises the hyperscale. So essentially, this is a hyperscaler grade infrastructure project, which any enterprise IT can take it, build a hyperscaler cloud, and I'll get into that. What that means is the scale is pretty high, and then build it out as part of the enterprise IT, and then realize the benefits of the efficiently managing the cloud resources as part of their IT. So key underlying, so CentOS is packaging, just like the analogy is OpenStack is a higher level packaging of sub projects underneath it, or Nova Compute or Neutron. Similarly, CentOS is a higher level packaging, and underneath you have different projects. Octos is our compute, just like OpenStack has the Nova. And Mizar is our new network virtualization project, just like OpenStack has Neutron. And Fornax is our edge cloud project, sub-project. And Alnair is our AI project underneath it. So that's kind of a higher level, the structure of CentOS is. So I'll talk about each one of them. So Octos Compute. Octos Compute is an open source project designed for large scale cloud infrastructure. And just to kind of set the background, Octos was evolved from Kubernetes actually. So we took Kubernetes and we essentially forked it actually. So because the way we see it, Kubernetes is not designed to be that scalable the way we want it to be. So that's the key thing. So we essentially evolved from Kubernetes, but we maintain the same. One of the great thing about Kubernetes is the way they have designed their API interfaces. So we kept all those API objects in the same way, basically, you see, just like pods and replicas. So you will have the same concept, constructs in our as part of our cloud infrastructure project as well. And so in order for us to be able to do that, we had to do major redesign of Kubernetes, actually, the real surgery, in order for us to be able to enable these 3 new features, actually. So the unified cloud infrastructure resource support. So if you look at OpenStack, very good for VMs. Kubernetes is very good for containers. But the key thing is, there are different types of workloads. So that's what we have done. So essentially, we unified the resource management across different heterogeneous workloads. It could be VMs, it could be containers, it could be bare metal, or it could be WebAssembly or unikernel or whatever. It's one way of doing it. Same kind of, if you look at, if you're familiar with the Kubernetes, we have like a pod-like abstraction, so everything kind of works off of that basically. And high throughput and low latency. So that's one of the reason. That's the paramount reason we ended up building this project from ground up actually, because the scale we want. Because a hyperscaler work at that level. There's currently in open source, there's no project that can measure up to that scale actually. So I'll get into what exactly I mean by in terms of what those numbers are. Multi-tenancy support. So multi-tenancy is a first-class citizen as part of our cloud infrastructure project. So that's built from ground up. So that's these 3 are the key contributions of our Octos Compute. Yeah, so this is a high-level picture of what Arctos is. So you can see that. Just going to summarize it. If you are familiar with the Kubernetes, so what we have done is Kubernetes has a control plane, the schedulers and all those controllers running, and then you have a data plane, KubeEdge, not KubeEdge, the kubelet. So essentially, what we have done is we have partitioned the control plane, actually. So partition the control plane, partition the data plane, and that allows us to provide scalability. So as the scale goes higher, you add a new partition. So that's how we, and at the same time, and if something bad happens, it doesn't bring the whole cloud infrastructure down. So it kind of localize, actually, you see. So if one partition goes down, it doesn't bring down the whole thing. So you have a resilience, scalability to go along with the resilience as well. So that's the key thing. So and we introduce new constructs which did not exist in Kubernetes, such as tenants, tenant partition, and the resource partitions as part of the overarching CentOS / Arctos compute architecture. So that's the kind of scale we're talking about, actually. So public cloud level scalability, it aims to support 300,000 hosts per region and 100,000 hosts per cluster. So that's exactly what I meant, when we wanted to build a hyperscaler cloud, OpenStack, maybe barely 5,000 nodes in a cluster. It doesn't go beyond that. Kubernetes, I know we've seen some effort. They've gone up to 15,000 nodes, but our goal is 100,000. So we already actually 60,000, the recent our performance numbers which we did. And now we are striving towards the 100,000 nodes in a cluster, actually. And this is how typically hyperscaler work. You don't have, so in order for you to have a hyperscaler level cloud infrastructure, because the OpenStack or Kubernetes doesn't let you go beyond 50,000 nodes, what you end up doing is you end up creating multiple clusters. So that model doesn't scale, actually, you see. So there's a management cost to it for each and every cluster. So you need a bigger cluster which can accommodate 100,000 machines, for example. So that's all control plane components are scale out and highly available. I talked about that in the previous slide as well. Tenant works are partition. Yeah, so multi-tenancy. So that's our second key attribute of our infrastructure project. Is multi-tenancy is a first-class citizen. Actually, it's built from ground up. So we have the tenant ID concept is going to flow through the entire architecture, of our platform. Essentially, if you're familiar with the Kubernetes, Kubernetes is built around objects and API objects. And there are two types of objects. One is the namespace-aware objects, and the second ones are non-namespace-aware objects. So the tenant ID flows through both, because unless you do that, you're not going to be able to realize the hard multi-tenancy as part of the overall cloud platform. So that's the kind of a goal. So essentially, we build the hard multi-tenancy whereby multiple customers can coexist and still be isolated within one instance of a cloud, one cloud instance, actually. So that's the hard multi-tenancy, isolation, autonomy, compatibility, and manageability, basically. So that's the unified scalability, multi-tenancy, and then the third characteristic is unified orchestration. I talked about that. So this is not only in a single pane of glass or one uniform way, we not only can orchestrate containers, but VMs and bare metals. And in future, we are already actually working towards WebAssembly as well as part of the same runtime layer, basically. You see. So it introduces native support for VM in addition to inherited from Kubernetes unified resource pool. So that's the kind of a key goal. That's the whole notion that you have different types of workloads but they get orchestrated the same way. Essentially, you orchestrating a pod, and the pod may be a VM pod, or it could be a container pod, or WebAssembly pod, or whatever. So we have a pod-like abstraction, if you're familiar with Kubernetes, actually. So that's serverless and bare metal. So next project is I'm going to talk about is Mizar networking. So Mizar networking is again the scalability issue, actually. So it's our network virtualization layer. We built it from ground up. Just like OpenStack has a network virtualization solution called Neutron. So we built out Mizar from ground up, and why we did that is because our goal was to be able to provision millions of endpoints in a fraction of a second, basically. So it's not just like a traditional you deploy a VM on a daily basis or an hourly basis. In a current cloud environment, you have all of these functions, serverless functions, containers come and go very fast. So you need to be able to provision these new endpoints in a fraction of a second, actually. So as opposed to hourly or a daily kind of basis, maybe you may want to deploy in a traditional way. In a traditional cloud environment, you typically deploy maybe 100 VMs or 1,000 VMs, but that's not the case because the cloud model is very dynamic. So you have all these functions, serverless functions. So that's why the current the network virtualization state-of-the-art solutions do not provide that kind of capability, the scalability to be able to provision millions of endpoints, in the cloud environment. So that's why we did that, and why we ended up building it very differently than traditional flow-based model. In a typical OVS, if you're familiar with the Open vSwitch, in a networks, the current network virtualization solution, you have a control plane that essentially programs all the virtual switches on all the hosts using a protocol called OpenFlow, actually. So that's how all the networks, basically all network solutions are. And the problem is the current flow-based programming are not scalable and have multitude of issues and quirks. Time to provision port increases significantly as the number of ports increase. Because if you have a subnet and you add a new endpoint, you have to go to all those other hosts and update the flow tables. So as you can imagine, if I have 100,000 nodes, I have to go and then I may have 100,000 physical nodes, and I may have thousands and thousands of endpoints. So if I'm adding a new endpoint, virtual endpoint, I have to go to all those hosts and update my OpenFlow, the flow rules, actually. So that's, you can see that why it doesn't scale, basically. See, high CPU utilization during flow parsing, packet traverse, multiple network stacks on the same host, provisioning time of new workloads. I already talked about the last one. So essentially, that's the problem. The provisioning, the current flow rule-based network virtualization solution, they don't allow you to be able to do provisioning of endpoints to that scale, basically, you see. So thousands and thousands of endpoints, come and go, basically, you see, in a very dynamic environment. So what did we do? So we built our network virtualization in a very different way. And this is the key enabler for that, actually. So the technology, I'm pretty sure a lot of you folks might be familiar with it. It's called XDP. XDP is the data path technology. It's a kernel bypass, actually. So the packets get processed at the device driver level itself without going through the kernel stack. So that's the technology we use. And what did we do, actually? So essentially what we decided was that we decided to do away with all of those virtual switches, MAC learning, and all that. And we built essentially network virtualization solution as a distributed system application, actually. And in the distributed system application, you have bunch of XDP programs, and they do all the magic, basically. So one XDP program is attached to the NIC. that processes all the ingress packets, this one. And then the other one is attached to the VF pair of the endpoint. This could be a container, it could be a VM, and that processes all the egress packets. And so that's the kind of that's what it is. I mean, there's simple. All of the packet processing happens at XTP level by these two set of programs actually. And the way they work is the way you configure these XTP programs is by populating the configuration rules using a user plane RPC interface in the eBPF maps actually. So eBPF maps are visible, to the user plane and the kernel's plane, and the XTP programs, they work on those configurations, and that's where you define your packet processing policies and all that. So that's kind of a nutshell, high-level summary. Flow programming model is great for programmable switches, but not scalable for multi-tenant cloud networks. Network provisioning throughput and runtime, CPU performance gains, create an extensible Mizar for cloud networking, unify the network data plane for VMs. So it's just like compute. It doesn't matter you're provisioning a VM endpoint or a container endpoint. It's a one uniform way of doing it. And one of the key things, why did we decide to do that, XTP, is this actually, you see. Because we want to take all our glue, all our cloud glue, for example, the network virtualization code base, and we want to be able to offload it to a SmartNIC, actually, the hardware device. We don't want to use any CPU cycles, to do that, I see. So that's one of our goals. So we are already kind of experimenting with it. So essentially, the whole Mizar XTP gets offloaded to a SmartNIC, and all the packet processing happens there. There's no trace of our code base at all on the physical host, actually. So the next project is Edge Fornex Edge Cloud. So that's this is the project we building it. Fornex is an open source edge computing framework for managing compute resources on the edge environment. It's designed to solve some of the key edge computing challenges, such as limited computing resources. You folks are all kind of familiar with this is the Edge conference, so same, the problem statement. And one of the key design goal we have is in an edge environment is different. The topology is hierarchical. So you may have a central cloud, and then you have a regional cloud, and you have a sub-regional cloud, and you have a leaf node cloud. So we are supporting that hierarchy, and I have a slide actually explaining that. And each node in the hierarchy could be of different edge cloud type, actually. So it could be a Fornex edge cloud, or it could be a Cube edge cloud, or it could be K3S. So essentially, our abstraction allows you to plug and play any different edge cloud platform. Fornex also offers high-performance virtualized network. The networking Mizar, which I talked about, we leverage the same the network virtualization as part of our Mizar, as part of our Fornex Edge Cloud project as well. Key features: computing nodes and clusters on the edge. Computing nodes and full-fledged clusters can run on the edge. Hierarchical topology, I talked about that, and I have a slide after that explains more. Flexibility, flexible flavors. So as I mentioned, so you can have a compute node, could be Arctos, it could be Kubernetes, it could be K3S, So edge networking, so we have the same VPC kind of a constructs available as part of our edge cloud as well, using our Mizar network virtualization. And this is what I meant by the hierarchical topology, actually. So you have a central cloud. This could be Arctos cluster, and this could be K3S, or this could be Cube Edge. And so essentially, you can build this hierarchy, your edge topology, basically, using this hierarchical model. So that's All-Layer AI project. So our focus of AI is not building algorithm, actually. So what we do is we do the system side of AI. Essentially, how do you make training efficient or the inference efficient. So whatever is needed for you to be able to do that, for example, when you're doing inference, when you're doing a training, you may want to share your GPU resources in a very intelligent manner, you see. So all of those things. Similarly, when you're doing inference, it could be a mix and match of CPU and GPU. So all of the system level functionality, we do that as part of our layer project. So we don't really build algorithm. We're not building like a new PyTorch or those models. So essentially, the enablement of the system component to run the AI models efficiently. That's our key goal, actually. So that's high level. All of these kind of sub-items kind of fall in that category. So these are the key features: elastic training, dynamic GPU allocation, GPU utilization profiling, and precise resource management. And one of the challenges, actually, if you folks have an AI background, so everybody understands that algorithms are important, but the whole data processing is very important as well. And the data processing are two different types of data processing. One is offline data processing. You do cleansing and all that before you start building your training your model. And then another is the last mile data processing, which essentially is when you're running your model, actually. You see, when you're training your model. And after each epoch, you want to do some data transformation. You want to change the data so that you can get predictable, your model is robust. So that's another thing we are looking at, and that's a pretty hard problem, basically. So it's not like an offline ETL or cleansing thing. This is like a last mile data processing. So there's a lot of kind of research work going on, actually, in academia as well. So we're working with professors on that topic. So optimized ML framework, parallelism optimization, hyperparameter auto-tuning. Okay, so that's pretty much the way CentOS, current CentOS, which we contributed, donated it to Linux Foundation. So that's the next version of CentOS we are currently in the process of designing and building out. So essentially, the model is very different. If you look at any cloud, AWS or Microsoft Azure or Google or whoever, everybody kind of works at the regional level. So essentially, if you want to deploy an application or get a VM, that VM would be part of it. You have to specify what region, East region, West region. So one of the key things what we are trying to do is we're trying to create a regionless compute environment. So essentially what that means is the problem with the regional approach is there's a resource imbalance, actually. So you end up having most of the workloads going to a bigger region, and other regions are sitting empty. So there's a lot of resource imbalance. So essentially, we want to create abstraction at the regionless level so that the customer doesn't have to worry about the regions as long as its SLA is met. So that's so as you can see that it's a pretty hard problem, actually. So before the presentation, before I asked that question, so you have all of these regions, and one of the region could be your edge clouds, so there could be multiple edge cloud. So you need a scheduler, actually, see, that has visibility to all of these resources available, and then efficiently it places those workloads to those cloud resources. So that's all of these components we're kind of building out the global scheduler. The way you build scheduler is not the same way you will find the scheduler is in Kubernetes. It's a pretty hard problem. So that's something we're building out. And then the key value store that goes across regions. So that's compute side of Octos 2.0 we're building out. And then Fornex and so Quark container is a new container we're building from ground up. So essentially, we got inspired by gvisor, and we took the similar design approach, and we built our own container using Rust language, actually. And it's much more efficient, much more lightweight, and we have done a lot of optimization. If you're familiar with the gvisor, it does syscalls as a function calls, basically. So that's where the performance overheads are when you start doing that, when you come out of your sandbox and you do your syscall. So we've done a lot of optimizations to mitigate those overheads, actually. So that's, and there's a lot of, we do TCP over RDMA over TCP. So we have pretty impressive numbers already actually. So we think that it's all open source. Everything is all open source. And these are all the edge and serverless. So essentially, we want to be able to have a programming model which is serverless based and uses our Quark container, lightweight container, as a container runtime. So that's pretty much done as far as the overall. And then we are Linux Foundation project. And just like any Linux Foundation project, we meet every month. We have a TSC. I'm the chair of TSC. And we have an advisory board, and we have a subcommittee and marketing. And everybody's kind of welcome and kind of explore projects or propose something. It's a very open, just like any Linux Foundation project. And these are the links. Everything is all there. Each and every project I talked about is all open source, and it's all there on these links. So that's about, I think the high-level overview is it's a pretty complex project, but I think 15, 20 minutes have been allocated. So this is what the high-level overview is. And with that, I'm going to hand it over to Prashant, and he's going to talk about the use cases, the business use cases aspect of Centaurus project.
Thank you, Deepak. Hello. So I'm not going to take more than 3 minutes or 4 minutes to explain the use cases with the Centaurus using in the healthcare. We talked about the metaverse and Centaurus in healthcare. You saw how elaborate the Centaurus platform is. So healthcare industry, everybody knows the challenge right now. Like it's like a car dealership. You go, you get a quote, and you actually have a guaranteed repair to yourself. But in healthcare, there is no health, there is no care. So how do we solve that problem? The problem statement starts from prevention to wellness for any healthcare purposes. And the cloud computing and the edge computing plays a very major role in determining that. So what we did is we took a use case of end-to-end scenario where we are able to basically move from all the challenges that currently we face, from the blockchain to data storage to every other things. And I'll quickly go over like what are the solutions we have built. We have built a solution that can capture the data from any watches, from Apple Watch to any watch, Fitbit and other things that can send the data from the edge site directly to the Centaurus. And within the Centaurus, we can perform the AI-related operations on that. You can see on the screen like any healthcare determines the data from neurology all the way to basically your cardiovascular, all the way going to the 6th level or 7th level of it. And that comprise of like collecting the data on the 5G, moving that data through the IoT devices to a location where it can be operated through the blockchain, through the quantum computing. I would have talked a little bit more on this topic, but I think in respect of time, I will cut it short and just move to the next topic. You can see that you can collect any sort of data sources from various things, and then you can actually aggregate it in Centaurus Cloud, use the AI algorithm. This is the architecture for the end-to-end scenario. And the way it flows from participants all the way to the consumer using the edge computing and the different pieces of regional cloud that Deepak has explained today is something flows like that. With that, that's all. I'll play a quick video if you guys were not in the session in the beginning. Yeah. Not really, Annie. Yeah. So in the movie, you can see the metaverse and the use case of the healthcare. It's a 1-minute movie. James is facing like a headache right now, and he is collecting all his data from his mobile watches in the real time, makes a call to 911. While his data has been transferred in real time to different pieces of compute networking, and AI. It has been determined that he needs a ER service in the meantime. The doctor looked through the metaverse into the different images, which is called as second doctor, where different images have been analyzed. They realized that it's a brain tumor that James is facing right now, and he needs a surgery. So during the surgery, they take all the data insights that's collected from the different variables, and you can use the CentOS platform to actually create whatever is showcased in this 1-minute powerful video. So the technology is there to change the world. Technology is there to handle the problems that you're facing. And the community is there, the source code is there. You are all welcome to use that. Thank you very much.